Very good evening, sir. Very good evening, Mani. Very good evening, Lakshmi. Okay, let's just start with the class, okay? So, first of all, wishing you very good evening, everyone. And I guess you already know this is going to be our sixth session on the same chapter, okay? So, let's just start with the class. Let me just quickly give you a brief what we already covered in the previous class. So basically in the previous class we discuss about a different kind of oxidizing reagent. There we discuss about that is a main that came in for oxidizing agent. Okay, or like K2Cr2O7 as a oxidizing agent, or the Jones reagent is there. Jones reagent, and then dry chromium oxide, and then PCC, and the last one is the copper and 573 Kelvin. So these are the like different kind mechanism and every point we already covered in the previous class. Okay, so in today's class, as we already discussed, the last topic is going to be the miscellaneous reactions. So what is the meaning of miscellaneous reaction? Like a type of reaction which is not the part of for any kind of mechanism, you can say. Okay, so let's just start with that part, miscellaneous reaction. So in today's class we are going to discuss about the miscellaneous reaction. So in this case, the first topic we are going to start is the pinacol rearrangement. So you can put 2 to 3 start. It's really very much important reaction. And then semi pinacol rearrangement there. Okay, so let's just try to understand actually what is the meaning of this word, that is a pinacol, pinacolone rearrangement. Okay, so let's try to understand this. Wait, okay, leave it. I'm going to explain it. Okay, so what is this pinacol, pinacolone rearrangement? So pinacol, as the name suggests, that something is connected with the alcohol, and then pinacolone. So obviously this part is connected with the one means ketone. So means from here that we are getting ketone, and we have to start with the simple, that is alcohol. Okay, sorted. So any kind of alcohol we are going to start? No. So we are going to start here, that is vicinal diol have to be there. So what is the key point? We are getting, or we want, that is a vicinal diol. Okay, we want vicinal diol at the end that vicinal diol is going to convert into the ketone part here. Okay, so this is sorted, that is a pinacol, pinacolone rearrangement. Okay, like ol means alcohol, on means ketone. So like we are going to convert a CO type of bond simply into the C double bond O there. Okay, like this. So let's just back again the slide where we just left about this. So let's start with that. Wait a minute. Yeah, here. Okay, so see this now, that is for example, like this is a kind of product we are having. Okay, let me just first give you a kind of general reaction rate. Wait, I have to change this slide. Okay, so let's just start that with an example. Let's suppose this is the example, this is a carbon carbon and we want diol. Okay, like this, and then this is a CH3, and this is some CH3 again, and this is the CH3 there. So this is a simple that we are just starting with this, and at the end what we are going to get there, that is a kind of ketone there. So let's just start with this. So let me just read the product. Wait a minute. Okay, I'm sorry for this. It's working now. Okay, so for this reaction what we're getting simply, that is a carbon, and it is a CH3, and this is also the CH3, and this is a CH3. I will tell you how we are going to get this, just wait. And this is a CH and a double bond. So this is the final product we are getting in this reaction. Again, what is the highlight point if you to observe that OH part is going to convert on in this part, that is the ol there. So it means 2H is going to react, and then we're getting one ketone. Yes. Now let's try to understand the mechanism. Okay, so in this case, if we are talking about the mechanism of the same reaction, then how about the mechanism there? This is really very much important there, mechanism part. So let's just talk about the mechanism for this phenol rearrangement. So in this one, the step number one, the step number one. So how about the step number one? Step number one means that first of all, let me just write again the same reaction. This is a carbon, and this is a CH3, and this is the CH3, and this is the CH3, and then again this. So the step number one is what? That is the formation of carbocation. So let me just write, that is a formation of carbocation. So first of all, we are going to form a carbocation. So formation of carbocation is the first step in this given reaction there. Okay, so obviously if you want to generate, if you remember, we'd already discussed about a kind of dehydration reaction. It means I'm going to use a kind of acid. Yes, H positive, any acid you can use. So let me just write here, so you can use any kind of acid in this type of reaction. Okay, this is like this. Yes, very good, Shiva. So yeah, so after so many days I am not aware about this, Mira. You know, may or may not be there. Okay, right now I have no information regarding this. So yes, you're right, that is basically you're having a diol and we are going to get a ketone there. Okay, so this is simple, this is how we're getting acid we are using. Okay, I hope now we're familiar. Once we are having acid, so what is really going to happen? You know, OH, OH, OH. OH has a lone pair simply. So this is the OH. OH has a lone pair. So obviously the OH is going to attack on what? That is H positive ion. So this is my OH ion. OH attack on this H positive ion. Cool then. So what we are getting, that is a CH3. First of all, try to understand the general mechanism. Then again, we are going to cover some important part as well from the mechanism. So first of all, this is a CH3, okay, and this is a CH3, and definitely this O now combined with two hydrogens. So what we are doing, nothing, that is simple. We are converting the OH into the very good living group. You know, once this OH positive generated, and okay, it's going to leave the molecule. So once it's leave the molecule, so what we are getting simply that this is a carbon and it is a CH3, and this is a CH3 and OH. So the step number one, I hope it is clear now, that is the generation of carbocation. So our carbocation is ready. Okay, so simple, the carbocation is ready now. So this is the first step, formation of carbocation. Now the second step is what? That is the rearrangement. Yes, this is the reaction where we are going to follow the rearrangement kind of reaction. Okay, maybe you will like, mom, see what is the use of the rearrangement? Okay, because if you're knotting something, let me just highlight this. If you're knotting something, that 2 CH3 here and here, right? And look at this, that is again that 2 CH3 here and here. So what is the difference between them? Wait, we will cover. Okay, just try to understand the mechanism. Let's just wait for a while. Okay, now the step number two, what? That is the rearrangement. So the step number two, that is rearrangement of carbocation. So the rearrangement of carbocation. Okay. So now, if we are going to follow the rearrangement, so which kind of thing we are going to follow? Remember everyone, that is a migratory aptitude. First of all, we are going to follow that is the migratory aptitude. So can you just tell me that what is the migratory aptitude if you remember from the previous classes? Yes, please, anyone. Very good evening, Niharika. Yes, anyone? Do you know the migratory aptitude? Okay, options are, for example, if let's suppose this is a carbon is positively charged, okay? So in this case, let's suppose maybe the phenyl group connected here. Okay, condition number two, maybe some CH3 group connected here. Okay, maybe some hydrogen group connected here. Oh, wait. Okay, like this. So my question to you, like out of, like, okay, this is positive charge, but should I have to go with the phenyl or the CH3 or a hydrogen? Means which one is going to migrate? This is the question. No idea. Okay, okay, maybe you don't know what. Okay, so be noted that we are going to follow this rule, that is HPR rule. Okay, HEPR rule we are going to follow in this migratory aptitude. Okay, let me just show the slide. This is how it's look like. So first of all, that is hydrogen, then aryl, then alkyl part. And in this aryl part, be noted that you have to consider the benzene ring which is connected with the electron donating group migrate first as compared to the withdrawing one. Look at this. That is the electron donating one is migrate first as compared to the withdrawing one. This is really much important. Okay, then next, if alkyl you are having, so you have to follow the tertiary, then secondary, then primary. So remember like HPR. So I don't know how you can make any mnemonic device, but just go with any and if you know. Otherwise, just be noted hydrogen first, then phenyl first, or aryl. Okay, or then alkyl system. So this is how we are going to follow the point. So let me just back again to our mechanism here. Look at this mechanism, right? So in this case, if I want to, change the like shift the positive charge. So how to? Wait, let me just write that the previous point here again. This is a carbon. This is a positively charged, and it is a CH3. Okay. So I know so many question in your mind, ma'am. See what is the point? Okay, why we are doing everything? Just wait. Okay, we will cover every question for you. Okay. So this is OH. Now this, look at this, like this is a first carbon, this is a second carbon. So what does it here? There's a no problem, like both are the methyl group. So sorted, that is we are going to follow, that is 1 2 methyl shift. So we are going to follow normally, that is the 1 2 methyl shift. Okay, cool then. So it's going to migrate here, and basically what we are end up there, that is this carbon has a positive charge, and it is a CH3, and this is a OH. Okay, and this is a CH3, and this is a CH3, and this is a H, CH3 again. So, can you just tell me, let me just try right, this carbocation, okay, or this carbocation? According to you, yellow or the purple one, which one is the most stable carbocation? Okay, let me just check the number. I guess it's difficult for you. So let me just write A or B. So according to you, A is most stable carbocation or the B is most stable carbocation? Yes, please. Anyone? I guess it's not difficult. It's a very simple, again, GOC type question. Hmm? A. A, okay. Okay, so let me tell you a very basic rule of the organic chemistry, right? So what is the rule? I guess you already know, if you're having a carbocation, right? So if you're having a carbocation, what is it? Obviously, it's planar in shape, and definitely that carbon is going to be how, that is a vacant orbit, right? So this is a carbon and this is oxygen. Maybe you don't know, but yes, it's really very much important concept. If carbon has a positive charge and if oxygen is there, so oxygen has a lone pair. And if you are going to count the octet, okay, let me just write, wait, like this, hydrogen and hydrogen. Okay, let's just count the number of electron for this carbon only. So one, two, three, four, five, and six. Total six electron. So you can say this carbon has a six electron, and we're discussing about the carbon have a positive charge. Okay. On the other hand, let's suppose this is my OH group. So how about the, that is the number of electron. So like one, two, three, four, five, six, and seven and eight. Okay. So it means octet is completed here. So then oxygen be like, let's do what carbon. I'm having a lone pair, you're having a vacancy. Why not we can share the electron? Carbon be like, not an issue because I want more electron there. So what is basically going to happen in this case? Oxygen transfer the electron to the carbon, and it's really famous phenomena. It's known as a back bonding. Okay, so although maybe you're having any tertiary carbocation, any benzylic carbocation, any kind of carbocation. This is the only carbocation which lead the scale. I know oxygen has a minus I effect, but still oxygen has a lone pair. So just because of this, that in this case, the oxygen participate in back bonding, and that's where the carbon achieve the octet rule. Okay, now let's count the number of carbon for the carbon, sorry, electron for the carbon. So observe this again, that one and two electron, because now it's a coordinate bond. Oxygen shared both the electron to the carbon. So carbon like I can count those electrons as well. So now total 8 electrons. So it's a octet is complete. So be noted, whenever the carbon is positively charged and it is connected with any species like oxygen, or let's suppose the halogen, okay? If you remember one of the famous thing, that is Marconic addition, there we're discussing so many time that if there is a triple bond and you want to add a water, then how to add? Okay, wait, I will explain what I'm saying. Okay, like this is also very stable. Okay, and one more, that is this is a carbon, and let's suppose the NH2 group is there. This is also really very stable carbocation. And why? Because you can say the plus M effect of these group, and it's a type of conjugation. It's a last type of conjugation if you remember the conjugated system. Okay, let me just explain what I want to explain to you. For example, if let's suppose you are having a carbon carbon triple bond like this. Okay, I want to add water, right? So you know very well, in this case I'm going to follow the Marconic addition. Okay, so let me just write some the hydrogen there so that you can get my point. For example, if let's suppose this is CH3 and this is a CH there, right? So Marconic said that is A or B. Okay, according to the Marconic addition, the OH is going to connect with this carbon and H positive here. Why? Because negative part is combined with that carbon where we're having a less number of hydrogen. So sorted then, if you're using 1 mole of water, let's say, so what we are getting, that is this is a C and the OH group is connected and this is a double bond NH. So now the second concept is what, that the OH is going to connect, wait, the OH is going to connect, the next OH is going to connect on a carbon number A or a carbon number B. This is the next question. So let's suppose if I have to follow the Markovnikh addition, so I be like, or you be like, ma'am, see this carbon has a zero hydrogen and this one has a two. So why not you can connect the two OH here? So look at this, that okay, although you're right, that is this is OH and this is a CH3 and this is a OH there, okay? Like this is how you can simply follow the mechanism, but try to understand the mechanism. What, actually how the mechanism look like, this is a carbon-carbon double bond and this is attacking on H positive ion, and then we are going to decide whether the carbocation is stable. So let's just suppose if my carbocation is stable here, obviously the hydrogen is going to connect here. Okay, then you will like, ma'am, why this carbocation is stable, or why this is the final product? Because it's simple. It's a OH group. OH group electrons stabilize this positive charge. So definitely the next OH is going to be the connect here. And hence in this case, what is happening, that as we already covered in the previous class, if you remember, that is a 2OH group. 2OH group simultaneously on a single carbon is never ever stable. So it's a knot. If you don't know about this, be noted that geminal diol is unstable. Okay, geminal diol is never ever stable. This is geminal. So with the quickly convert, and what we are getting that is a CO and CH2. It's a kind of mechanism from where we are getting a ketone from a carbon-carbon triple bond. Okay, so be noted, it's really very much important phenomena. Let me just back again. I hope now the rearrangement step is clear for everyone, like why we're going to rearrangement. Because the main purpose of the rearrangement, because we want stable carbocation. So OH be like, now don't worry, I can stabilize this. Okay, yes. So that's it. This is the only main purpose of the rearrangement. I hope everyone you're getting my point. Okay, any problem with the rearrangement point? Let me know if you're having any problem. Okay. So let's continue again. So let's see the third step, that is the deprotonation. So deprotonation means obviously the proton is going to escape. Why? Because we don't want OH group. So let's understand actually now what is going to happen in this case. So this is a carbon, and all CH3 groups simply now connected here. Okay, and this is a CH3, and carbon has a positive charge, so oxygen has a lone pair. Oxygen will like, hydrogen, it's time to leave. Okay, so hydrogen will like, not an issue, I'm not having any kind of respect in the complete chemistry, so don't worry, hydrogen will like leave. Okay, so the last step is what, that is the deprotonation. So the last step is going to be the deprotonation, simply that proton is going to release. Okay, deprotonation. So that's it, sorted. And hence, what we are getting simply, that is this carbon got the double bond oxygen, and this is a CH3. Oh yeah, it means we are ready with the ketone. So that's it. This is a three-step reaction. Let me just quickly give you a brief. Step number one, the formation of carbocation. Okay, this is how. Step number two, that is the rearrangement of a carbocation. Step number three, that is the removal of proton or the deprotonation there. So first of all, it's your turn. Any issue with the mechanism, please let me know. Any step not clear at your end? Because now it's my turn. I'm going to ask you some questions, okay? You know, teacher are explaining something and then asking the different type of question. So the same thing I'm going to do now. Any problem, please? Okay, please then let me know if you are having any problem. So now let's try to solve some problem. Problem number one. Okay, so the question number one, you can say. This will be a question number one for you. I'll answer this, please. Okay, so wait. Okay, now so let's go with the question. Okay, we want like what will be the answer for this question. Okay, so how to proceed? First of all, as we know, like now you know the mechanism. So step number one is what? Formation of carbocation, right? Cool. So formation of carbocation is the step there. Now my question to you, so which OH is going to protonate first? Like maybe this OH or maybe this OH. So in the previous one, we are having symmetric OH, but now we are having asymmetric OH. So which OH is going to protonate first? Is it A or is it B? Think about it. It's easy. Okay. So Hint for you, we are going to check it for the stability of carbocation. Okay. So the step number one is what? Formation of carbocation. So should we to go with the A, OH or the BOH? This is my question for you. Okay. Everyone, please answer the questions. You know the first rule of the organic chemistry. You know the answer of everything. Okay, BN. But why not A? Okay, you're right. B is the correct answer. But why not A? This is my question. Okay, so yes, very good, although you're right. So option A, B is the answer here. But how? Let me just do what? First of all, let's protonate the A, okay? So if you have to protonate, I'm sorry, protonate the O. So what we are getting there, that is this is a positive and this is going to leave. Okay? So once it's going to leave, what we are getting, let me just simply erase this. We are getting this kind of carbocation. So carbocation will be like CH3 will be like okay. But NO2 will be like, hey, what are you doing? I am a electron what? Which kind of group? Electron withdrawing group. Okay, this is a choice number one. Okay, now let's discuss about this. If this OH is going to participate, so this is the next carbocation, the green one focus on. Okay, now OC is, there is a common thing. And how you are comparing the thing here? See, this is a common part. CH3 is a common here. What is the different thing here? The different thing is this. This is a NO2 group and this is a OCH3 group. And now this is the point. This is the thing that we want to compare here. So what is the case? That this is electron withdrawing group and this is electron donating group. So this side be like we are able to handle the positive charge. So just transfer the positive charge to us. So hence that is the correct answer for this question be like this is going to release. Okay, sorted. So let me just again write this. Okay, I hope this part is clear for you. Okay, so this OH will remain same and this is the first step. Carbocation is ready now. Okay, now total we are having a two thing. We are just left with the two thing and you will tell me which one we are going to migrate. Let me just check again. Okay, between this yellow you have to decide. So it's a and B. So which one we are going to migrate? This is the next question. Benzene will be the positive one. No, although if you're asking about the activating and deactivating, benzene is a deactivating group, Neharika. Okay, benzene is a deactivating group. But deactivating is not going to play here. Important is what? Resonance, conjugation. If the benzyl carbocation we are having, so the benzene participate in the stabilization of that positive charge, Niharika. So we are going to give the priority to the stabilization or the conjugation. Yes, please. Which one I am going to migrate? A or B? We just discussed the migratory aptitude if you remember that we are going to follow the HPR rule, right? If you know. So please answer this question. Should I go with? Okay, I'm sorry. Okay then. So which one? A or like which one we are going to migrate? A or B? Okay. Just answer the question, please. What is the problem? You're not getting the point because your response is very slow. Okay, no need to say sorry, okay? Okay, I will explain. Okay, I will explain. Just wait, okay? Let's just first understand this question and I will explain the previous question to you. Okay? The triple bond one, Lakshmi, right? Okay, Kaurav or Yashashvi. What is your real name? Should I call you Kaurav? Yeah, of course, I will explain to everyone. Just wait, okay? Welcome to the class. Not an issue if you are a new. I'm going to say the same thing. Ask anything if you want. Yes. Yes, I'll be okay. No. So which one means the stability of the positive charge, Lakshmi? Just please confirm. I will explain, not an issue, okay? Okay, wait. Okay, so let's understand actually what I want to explain, okay? Let me just erase this complete part, okay? Okay, so this is the wage, okay? So wait. Look at this. If B is going to participate, okay? So let's just tag this is A or this is B, okay? So let's just suppose B is going to participate here. So what is happening? This OH has a lone pair, okay? So I hope you know how the mechanism going to follow. This is going to attack on the H positive ion, okay? So it means this is H and this is a positively charged, okay? So it is going to leave. Okay, so once it is going to leave, what we are getting, okay? Just for your convenience, I am going to raise this air, okay? To try to understand. Now, if this we are getting, so this carbon has a positive charge, okay? It is a CH3 group, and this is a simple NO2 group, okay? Like this. Or this is a CH3, and this is a OCH3 group, okay? OH. This is a condition number A, or the B, I'm sorry. And how about the A? Let's talk about the A there. If we are following the A, it means again this time this OH is going to protonated and this is H positive and this is going to leave. Okay, simple. So what we're getting now again, this is a phenyl ring and it is a NO2 group and this is connected with the CH3 group and sorry, CH3 group and OH. And this is a carbon, it is connected with the CH3 group. Okay, wait, if let's suppose my video is blocking your way, I will change the position. Okay, it's a OCH3 and this is the positive charge. Okay, now let's compare between these 2 points. Okay, so let me just highlight the which point we are going to compare these two. Okay, these 2 points we are going to compare. So let's try to understand actually really what is going to happen. So which positive charge is most stable? Okay, so let's compare the common thing between them. Okay, so let's compare the common thing. Common be like, for example, if you to observe this carbocation be like, I'm having CH3. This carbocation be like, what is so special? I'm also having a CH3. Okay, then the second point, that this carbocation be like, I'm having a phenyl. So this carbocation will be not an issue. I'm also having a phenyl ring. But look at this, what is the new point here? That in this case, this NO2 is a electron withdrawing group. So NO2 be like, I'm going to take the electron density. Okay, so now in this case, what is it? This is a OCH3 group. So OHCH3 group be like that, it start giving the electron density to the benzene ring. So now this benzene ring be like, I'm less electron denser. Why? Because my electron density is taken by the NO2. So directly indirectly we can say this is less electron rich, right? And this is the more electron rich pieces, okay? So this is more electron rich. So if this is more electron rich, so definitely, you know, positive charge stabilize with the donating one. So I hope now this point is clear for you, that which carbocation is more stable. Is the NO2 one or the OCH3 one? Because you know, NO2 one is what? That is a plus M group. We know, right? So let me just write all the effect that is shown by the like, this group. So it's what? That is, it's a plus M group. It's a plus HI group, and this sorry, plus M group. That's it. And in this case, this is a minus M group. Okay, I hope you're getting my point. That why this carbocation is more stable or the NO2 one. Okay, Lakshmi. So is this point clear or still any problem? Okay. I hope it's clear. Still not clear? Don't worry, I am explaining one more time. If you are not having any doubt, let me know, please. Lakshmi, if you are there, please confirm. Otherwise, I will explain one more time. Okay, Devesh. So let's continue now. Okay, so let's start now. So I hope the first step is clear for everyone. Which carbocation is more stable, right? So now we are ready with the most stable carbocation. It means this is the most stable carbocation. Okay, let's back. Let's move to the next slide. So after once we are getting a most stable carbocation, so what we are getting simply, this is a carbon, and it is a positively charged. Okay, so the step number two, if you we just discussed, that is the rearrangement. Rearrangement we are going to follow. So CH3 is a common part again. And now my question to you, which one we are going to migrate? Is this okay? Let me just check again the group number. So step number two, that is a rearrangement. Okay, so obviously OHs have to be there. So which one is going to migrate? Is it A or is it B? We just discuss about the migratory aptitude. Anyone? Which one we are going to migrate? Okay, Lakshmi. So recall the rule. We just discuss about the migratory aptitude, like which one is going to migrate first. Yes, please. Okay, let me just write the rule one more time. So what will be the rule? That we have to migrate hydrogen, then phenyl, and then aryl or the methyl system, or let's suppose the alkyl system. So this will like I am phenyl, okay, or this is what, this is alkyl system. So which one is going to migrate? This group is going to migrate. Okay, this group is going to migrate according to the migratory aptitude. So hence that it's migrate from there to there. Okay, so once it's migrated, what we are getting, that is now the carbocation is here. Okay, so let me just write the carbocation like this. Okay, maybe you are having a problem then. So this is a positively charged, it's a CH3 NOH. So we are getting now a very much stable carbocation is ready. Okay, so it's a OCH3. And then again that one more phenyl is connected here, okay, like NO2. And the next step is what, quickly, that is again the deprotonation is there. Okay, so I hope you know now what is the next step, deprotonation. And what we are getting, that this carbon got a double bond and it is a CH3. So we are ready with the product. Okay, so this is how we are getting that. The answer for this question is this. Yes, this is the answer for this question. Okay, so this is the correct answer for this question. One more, let's try one more question. Okay, first try to understand the mechanism, then I will tell you a shortcut as well. Okay, but you know, shortcut in the very first is not good for your health. So better to solve step by step. Now, this is a question for you. Answer this question. For this question, okay, 2 minutes. Okay, just try to answer the question. 2 minutes for you. Let me just write the options, like what is the correct answer for this question. Okay, so option number one. There's a no space. Okay, you to solve. Don't worry. Okay, that is only this is the space, right? So just let me know between A and B, which one is the correct answer. Okay, will come, not an issue. Chat is not working. Yeah, yeah. Actually, that's why I'm facing the problem. You know, I guess my audio, video, everything is lagging with your chat. I know, Lakshmi, this is the point. Yes, please. A is the correct or the B is the correct here. If you are smart enough, A is not a feasible answer, you know? Yes, Shiva and Niharika. Come on, if you are observing, you know, you can solve this question smartly if you don't know the mechanism even. Look at this. That one, two, three, and four is there. Okay. So like how it is possible in this case? Let's understand this point, okay? So let me just explain. Let's wait, like BB. Very good, everyone, okay? So let's try to understand this question again. So, okay. So what is the question? You will be having a two phenyl ring. Quickly let me know like which where we are going to form the carbocation. Okay, let me just write it's a phenyl, okay? pH only, so that we can make it quick. Okay, it's a phenyl normally, okay? And this is OH and it is hydrogen. Let me just check the question. Wait. CS3. Okay, first answer this question, A or B. Which one is we are going to protonate? This answer this question quickly. Which one we are going to protonate? A or B? Which one? Check it for the stability of carbocation, right? Of course. Okay, Shiva. I will explain the expansion one as well, okay? Just wait for a while. I will. A, okay, so we know why? Because see, once if the carbocation is generated here, so definitely it is going to be the stable one. Why? Because the two phenyl ring, more is the resonance there. So once the carbocation is ready, the next step is what migration. So which one is going to migrate here? Definitely that is the C. Why? Why? Because HAPA rule are going to follow. So what is happening? There's a 1-2 hydride shift. There's a 1-2 hydride shift, and then what we are getting there? So it's a pH and a pH and a hydrogen and then positive charge. So once the positive charge, they just simply form the double bond. Okay, so this is the final answer for the question. So let me just check the options there. Sorry, not the slide. Yes, so what is the correct answer? Option B is the correct answer here. Okay, so very good, everyone. Now, as you ask about a ring expansion type question, let's just solve a one type of question like this. Okay, so for example, okay, let's suppose I'm having this five-member ring. Oh, wait a second. Okay, this is a five-member ring. Okay, and let's suppose OH group is connected and OH group is connected. Okay, like this is the question. Now, so in this case, both are like this is a five-member, not an issue. Which one you want, you can protonate. Okay, so let's just suppose I'm go with this. So again, this is a protonation and positive charge generated, and what we're getting that this is going to leave. Normally, this is going to leave. So what we're getting then? We are getting it's a five-member ring. Okay, and OH is still connected here. So this is the OH there, and now this is a carbocation there simply. Okay, so this is a carbocation. Now, as we know, the rule of the chemistry that six member ring is more stable over the five member, and more stable over the three member, and more stable over the four member. This is the stability order. Okay, five, six, then five, then three, and then four. Don't say, ma'am, then why the four is there? Because you know very well the four member ring is a puckered form and the highly unstable one. Better three member is better over the five, four member. Okay, so this is a different point. Now, listen my point here that actually, if you remember in the previous one, why we're migrating the thing? Because we want stable carbocation. Okay, we want stable carbocation there. Okay, let me just do what? That look at this. This is a positive charge. It's a five member. So if it is possible, we are able to expand. Why not we can expand this? So let's see how to expand this. Let me just write the five member be like this. It's a five member. Try to understand my point. It's a five member ring, and then there's a positive charge like this. Okay. So in this case, what is happening there? I hope you know the rule of the migration there. So this is how that simply this ring is going to expand. Let me just write how. Okay, first let's just shift the carbocation. Okay, migration, then it will be better for you. Okay, let's just first do what? Rearrangement. Wait. So in this case, what is happening in a rearrangement? This is a positive charge. If this is a positive charge, then okay. So in this case, like, wait, I'm not getting how to explain it. So this is a five member. Okay, just This is a 5 member, and this is a positive charge. Okay, or wait, let's just see, this is OH1, and here we are having a positive charge, and again it is connected with the 5 member. Okay, like this. Just this is the point. And in this case, like how to expand the ring. Okay, so whatever be this point here, okay, and this is a simple this bond here. So how to expand the ring? So you have to imagine like your bond break be like this. Okay, if you don't know how to expand the ring, whatever be the positive charge with respect to this is alpha and beta. So we are going to only expand alpha or beta position. Again, I'm repeating that this is a positive charge. With respect to the positive charge, next carbon is alpha and then beta. It means the ring expansion or ring compression is just a 1, 2, and 3 carbon game. 1, 2, and 3. 1, 2, and 3. Okay, so this is alpha and beta, or 1, 2, and 3, which whatever you like, you can use there. So in this case, what is happening? That look at this. This bond is going to break like this, and hence that in this case, this carbon have negative charge, and this is a positively charged. Okay, negative and positively charged. And obviously if it is this is negative and positive charge, let me just resolve the thing. So what is happening there? This bond break. Okay, wait, I will explain that this bond break, and once this bond break, so this positive be like, why not I can connect with the negative charge. I'm repeating one more time, don't worry about this. Okay, so again, this is a 5 member. Okay, this is a 5 member, and then like this it's break negative positive, and simply combine this and this bond break. Okay, so we're ready with like 6 member ring. Now let me just write that the number here. Okay, so better to write the number for these kind of cases. So let me just write the number, like it's a 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon, 6 carbon. Okay, so let me just make a 6 member ring now. So it's a 1, 2, 3, 4, 5, 6 member. Okay, so again that, okay, let's just write the numbers. So 1, 2, 3, 4, 5, and 6. So look at this, at first position there's a 5 member ring connected here. Okay, so this is how the 5 member ring connected. Okay, this is how the 5 member ring connected. And at which position? At the second position the OH is there. Okay, so it's what? It's a positively charged. It's a positively charged. Still one more chance for the expansion. Okay, so first of all you will know, you will tell me the first point is clear. Voice is low. Is the same problem with everyone? According to me, it's not going to be there. Hello? Or someone A said like, okay, audible clearly. So first of all, is this point clear? Like, like how to expand the ring or not? No, it's not 10 member, okay? You know, it's a 6 member separate and 5 member separate. Okay, it's not 10 member ring. It's not 10 member ring. Okay, 10 means when both combine, then it's become 10 member. Okay, so this is a step number one. So how many time we just expand the ring? First time. You know, which kind of question asked from this type of question? How many time the ring expand? Or how many time the rearrangement is going to take place? Okay, so one point is complete now. That is we rearrange this thing first time. Okay, let me just write quickly the product what we're getting after the rearrangement. So it's a 6 member ring. Okay, it's a 5 member ring. Another positive charge here. Okay, if you have to observe something again, let me just highlight only that part which one we are going to expand again. Look at this. Let me just expand this yellow. What is this yellow? So it's this is a yellow, and isn't it the same? That is a positive charge. Look at this. Again, we are having one more chance for what? That is expansion. Okay, and obviously the OH is going to be there. So let's expand again. Okay, let's expand again on the next slide. Okay, so let's just back here again. So again, which we are going to expand now, this point we are going to expand. Okay, this portion normally. Okay, so let's try to expand now. And what you have to do, obviously you also try this, okay? Because in the very first it look little bit tricky. So again, let me just write the numbering. So search for, this is my positive charge, right? This is my positive charge. So it means where the expansion is going to take place. So let me just try, like this, and this point is going to participate in expansion. Okay, so let's see how that this is going to break. This is going to break. Okay, or better to use this side, right? Because that side we are having issue with the 3D. Okay, so look at this one. Just wait for a while. Let me just tell the OH you to stay here. Okay, so this is like this, and then this is how the bond break. And just imagine, okay, like this is a negative charge and this is a positive charge. Just try to imagining the thing like this. And again, that you can say this bond break. Let me just erase this bond. Done. Okay, and then which one is which point is going to connect now? So this and this point, this and this point is going to connect. Okay, so where we are having a positive charge, so now my positive charge simply shift here. Okay, positive charge simply shift here. So I'm erasing all the thing now. Try to understand my point. Okay, this is a positive charge. It's a positive charge now here. Again, let's count the number. So it's 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon, and 6 carbon. Okay, so it means we're having a 2 6 6 member ring. So what we're getting, that is a 1 6 member ring, and just that is one more 6 member ring. Okay, one more 6 member ring like this. So let me just give the numbering, right? So it's a 1 1. No, it's 1, 2, 3, 4, 5, and 6. Okay, like this. And at the sixth position, the OH group is connected. And at the first position, the positive charge is here. So right now we are ready with this 2 6 member ring. 2 6 member ring. Okay, now how many time we rearrange this? That is a 2 time. So let's just back again. So it means now I have to show this quickly, right? Then how it is going to happen? This bond simply migrate. It's a, you can say advanced type of migrated reaction. So let me just write quickly. It's a 6 member ring like that. Okay, it's a positive charge and it's a OH ion. Still, it's not stable. Okay, now we are going to follow the third type rearrange. So how many time we already rearrange? That is the first time rearrange, second time rearrange. Now let's rearrange third time as well. So how about the third time? Third time is sorted. Okay, now again look at this. What is it? It's a hydrogen. So now hydrogen is going to migrate. So this hydrogen migrate from there to there. So what is the third product or the third type we are getting there? It's a third time rearrangement. So it's a six member ring. It's a six member ring and a sorry, and a hydrogen simply here, and this OH. Okay, once we're getting a OH, so what is the simple case? That is a double bond is going to form here. Okay, so this is how, wait a second, one, two, no, 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 because only four, no, it's not possible, wait. One carbon, two, three, and okay, already there's a four bond. So how it is possible? OH is there, it's a six member, and there's a positive charge here. So 1, 2, and 3 positive charge. So with respect to this is a hydrogen. It is going to migrate positive, 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 positive. No. Okay, leave that. This is the final product because it's not possible. The third rearrangement is not possible here. Let me just back again here. Okay, positive charge and done. Because for that one, for the next step, the ring is going to open. Okay, so that is the another point. We are not going to cover this here. So it's a five member ring and a double bond. This is the final product for this reaction we are getting. Okay, uh, let me explain why I'm not considering the previous one. So I will explain this point as well. It's a six member ring. Okay, and this is a six member ring. And if this is a OH, so this is a OH and there's a positive charge. You know how the thing is going to happen? This double bond attack here and this ring open up. This bond is open up, and what we are getting then, we are getting this is a this kind of product. Okay, and then double bond. So this is the final product for this one we are getting. Okay, so For this one, most of the time in your question, this is the final product, so don't worry about this. If you want to follow that step as well, so in this case, like bring open up. And now how many carbon we are getting? One carbon, two carbon, three carbon, four carbon, six carbon, seven, eight, nine, and 10. Someone's told me about this, like we are getting a 10 member ring. Okay, I don't know the name. I hope this is the point. Okay. Uh, yes. I hope it's clear now. Okay, not stable because it's a positive charge. Okay. I maybe you're saying that is a predicted rule is not going to follow, right? You are going to tell A, right? So yeah, this is not stable. That's why you know that the ring is open up. See that we are getting 10 member ring at the end. Okay, is this point clear for everyone? Like actually, what is the final answer? Yeah, it's a kind of yeah, already know. Yes, Siva, you're right. Okay, so but most of the time for the pinnacle rearrangement, the step is enough for this only. Okay, so if it is given an option, so just go for that. Okay, if it is given in the option, so just go for it. But most of the time, more than enough for you. Okay, otherwise, this is the next step. This kind of question asked in advance, not for the main, according to me. Okay, so I hope it's clear for you. But the question, which type of question asked, like in this case, how many time we are going to rearrange the thing? So answer will be three. Three. Okay, three time total. Okay then, so I hope it's clear for everyone. If still not clear, just watch the recording and then keep rewinding the thing and then you'll try to understand my point. Okay. So anyway, actually, it's an extra question for you asked by the Shiva. That's why I'm explaining, okay? Not our part, not our part here, okay? So let's just back again. What we're discussing, Phinacol rearrangement. So this point done, and okay, that is this we already covered, right? So look at this OH, and this one we are getting, and then okay, this is a three-step reaction. It's a formation of carbocation and then rearrangement and deprotonation, okay? So now let's talk about the next one, semi-pinacol. Okay, so the last topic of the class that is a semi-pinnacle rearrangement. So something is connected with this word semi-pinnacle. Okay, so let's discuss about that is what is so special about that is a semi-pinnacle. Okay, pinacolone rearrangement you can simply say. So semi-pinnacle we are having and it is going to convert into the pinacolone. Okay, now just answer this question. Okay, because we already covered. I want to check something. If let's suppose this is NH2. Okay, if let's suppose it's NH2 and I am adding NaNO2 plus HNO2. So what you are getting here? Answer this question, please. Options are we are getting BDC means benzene diazoxide chloride or phenol. Two options for you. Whether we're getting phenol or benzene diazoxide chloride. Yes, please. What we are getting here? Option A, is it benzene? Okay, let me just write the option better for you, right? So option number one, if you remember, that is the Scotton, not Scotton, that which chapter? Haloarine and haloalkane. There we discuss about this. Schmidt reaction and or okay, there's a two naming reaction. Getterman reaction. Yes, yes, yes. So this is the case. N2 positive and Cl negative. So it's a benzene diazonium chloride if you remember. Okay. Or the condition number two. So we are getting this. Or what is the correct answer? A or B? Benzene diazonium chloride hitting above. Okay, Shiva, although you're right. Okay, but okay, this is simple point here. Okay, now let me just change my equation and then again answer the same question. Okay, so in this case, if let's suppose I'm having only R into, okay, let's just use some R, R be like, it is a CH3, it is a CH2, and then NH2. Okay, still, I'm using the same reason HNO2 or NaNO2, okay, and then same. What are the options? Okay, so like this is the thing that we are getting N2 positive Cl negative or CH3 CH2OH means again the same question, we're getting alcohol or benzene diazine. Which one is the correct option here, A or B? Yes, Andmere, you're right. Please answer this question then. A or B? Which one is the suitable answer here? Ethanol. Okay, do you know if temperature is not mentioned? Generally, what we are going to do this. And in this case, what is the temperature there? The temperature was 0 to 5 degrees Celsius there. So listen my point. Okay. The step number one is what? That formation of this thing. Formation of this thing there, it means we are getting CH3, CH2, and then N2 positive. But if you are having alkyl system, so N2 is going to leave, right? And what we are getting CH3 and CH2 in positive charge. Okay, and you know very well what is the reason behind that N2 is going to leave, because N2 is a gas. And this question asks so many time in a PYQ that when you are using an alkyl amine and if you are using NaNO3 or the nitrous acid as a reagent, so we are getting like N2 as a gas or NO2 as a gas? It's a really very much important question from the previous years. So what will be the correct answer for this question? The N2 is going to be the correct answer, not N2. NO2. Sorted. So it means N2 is going to release. Yes. Now once there is a formation of carbocation take place, so the second step is what? OH is going to connect here. So definitely in alkyl system, we are getting the final product as alcohol. Reaction never ever stop till this N2Cl negative. But on the other hand, if I go with the benzene part here, so in this case, think about it. If there is a direct positive charge on a benzene ring, we discussed this thing so many times. Direct positive charge on a benzene ring, highly, really unstable. Benzene, once in a while, okay, can handle the negative charge on its surface, but positive charge on benzene ring never ever stable. So in this case, BDC will like, okay, I'm not go with the phenol. But you know that when we're increasing the condition, like if you're changing the temperature, so many times we're discussing when you're forming BDC, you have to make sure the temperature is 0 to 5 degrees Celsius. Why? Because if you're increasing the temperature, we are getting a phenol, and that is not visibly we want there. Okay, especially in for dyeing processes, don't worry, again we are having a chapter, separate chapter for the nitrogen family, there we're discussing, but it's a very famous food process for dyeing. Okay, if you form a dye, so that's why make sure 0 to 5 degrees Celsius temperature should be there, so that it's not going to break further, it is not going to form phenol at high temperature. Okay, anyway, I hope you are getting my point. So why I'm telling you the complete story, because I want to explain to you the semi-pinacolone rearrangement there. So let's try to understand what is really the semi-pinacol rearrangement. This is my point. Okay, so let's discuss some cases. Ditto, copy and paste. The only simple, the very small difference is what we are going to discuss. Wait for a while. So let's suppose again you're having a carbon and this OH. In the previous one, in the complete phenol rearrangement, we are using both OH, both OH. But in this case, this time you are having some different group. Okay, you are having some kind of different group there. So for example, if let's suppose this is my CH3 and this is my CH3, and okay, this is again the CH3 and a CH3 there. So let's suppose this time I'm using NH2. Okay, and I am using some NaNO2 or HNO2 again. Okay, so what is going to happen there? The step number two, same ditto. That first step is what? Formation of carbocation. How there is a formation of carbocation? Because look at this. This is CH3, and OH is there. And this is a CH3 and this is a CH3. So N2 be and NH2 be like, I am going to convert in N2. So N2, what we just discussed, it's going to leave, and quickly once it's going to leave, we are getting a carbocation. So what is the different point in a Samipina rearrangement? That this time we are using one is a very good loving group. Look at this. Okay, this can be any group. This can be any G group other than OH. NH2 can be there, chloride can be there, or any group can be there. So the step number one did to that formation of carbocation. And once the carbocation is ready, same migration, and then again we are getting a ketone. Let me just write again the final product. What we are getting simply, that is the double bond. It is a CH3. Wait, I will change the position of my video. Wait for a while. And it is a CH3, and it is a CH3, and it is a CH3 simply. Okay, so if you're noting something there, look at this. Okay, the product is ditto. What is the extra point? The NH2 group is there. This is the extra point. Okay, let's see more examples. Okay, let's see more example there. One more example. Okay, for example, that if I'm having this in this, okay, okay, let's just write CH3 and a CH3 and OH again, and it is a CH3 and a CH3 and OH again. What if I'm using sorry, What if I'm using AgNO3 there? And let's see the chlorine is there. Chlorine will be like AgNO3, and as the AgNO3 combine with chlorine, what we are going to get there? That is AgCl, precipitate. So quickly the chlorine will be like, leave, precipitate. I'm going to precipitate then. Okay, so means what is happening? Chlorine is definitely going to leave, and we are getting a carbocation again. So this is how that if we are having any Z group other than the OH, like chlorine in this case is NO3, or like in the previous one we are having an H2 and an N3 and an HNO there. Simple agenda here is what, that formation of carbocation is the sorted main motto here. Okay, is this point clear for everyone? Like how to go with this? Okay, this is all for the semi-pinacol rearrangement. Now your turn. Any problem or any doubt in this reaction, let me know. Okay, so semi-pinacol be like other than the given thing. If we are having any Z group can be there other than the OH, but at least one OH is the key point. Okay, let me just check any like kind of question if I'm having. Okay, let's solve the last question. Okay, then we're going to end the class. This is the question for you. Just try to answer the question. Okay, this time the one problem is automatically solved. What is the problem? Like we are not going to select which carbocation is most stable, because we are going to make sure that this group definitely going to live, right? So this time issue is already sorted, that which OH we are going to select is not the actual issue here. So now, if in this case I'm using again that the same reagent HNO2 or NaNO2, yes, and heat this. Let me know what will be the final answer for this question. Okay, options are option number one. You can solve this question by elimination method as well. Technically, it's not possible, right? Let me just change this. It's option number A, okay? Option number B, okay? And C, three option only. Last one is the not these, okay? You have to identify between these three options only. This reaction is really very much important. So again, after the class, try to understand and apply once, try to draw the mechanism for this reaction as well. Yes, please. And these, none of these, okay? Let me just write the end at the very top. None of these, okay? Okay, last answer. Answer this question, please, everyone. Yes, please. What is the correct answer here? Okay, Lakshmi. I'm waiting. I know it's a little bit lengthy question, okay? So, 2 minutes for you. Okay, sure. Okay, Niharika. If you're answering B and C, it means at least you're getting the point, right? I'm not assuming like you have to answer the question correctly, okay? Maybe because it's right now it's going to happen. So let's try to understand, okay? Okay, not an issue. So let's try to understand the question. Okay, first of all, look at this. This group is going to convert into the N2 group, right? We just discussed. So definitely it is going to leave. Let me just erase this. And hence we are getting a positive charge here. So if this is a positive charge, so definitely this double bond here can't be possible. Option A, out of the box. So that's why let me erase this. This is not the correct answer. So if this is a positively charged, now here which group is going to migrate? Okay, so which group is going to migrate? Is this A group or is this B group? As we already discussed the migratory aptitude, let me just explain or rewind. This is the migratory aptitude, okay? We already covered if you remember. Look at this. I already highlight to you that if a benzene connected with electron donating group migrate first, then normal phenol and then NO2 group. Okay? Or the withdrawing. It's not NO2 is the fixed point. Any withdrawing group can be there. Okay, so let's just back again. The point where we're discussing every point here back here. Okay, so in this case, what is the point here? Look at this. This is electron withdrawing group if you're observing, okay? It's electron donating group. I'm sorry, withdrawing, not donating. So between A and B, which one is going to migrate? So definitely this group is going to migrate here. If this group is going to migrate, then what we are getting? Okay, after the migration one, what we are getting? Uh, Definitely this. Okay, C is the correct answer here, not B. Okay, so is this point clear to you, that Niharika? So this is the correct answer. I will explain the last step as well how. So see, this is how the positive charge generated here. And once the positive charge generated, we are getting a normal, that is a deprotonation and it's double bond here. Okay, so this is how the answer for this question is this option number C, or this is the correct answer. So in this reaction, what is the important point? First of all, you have to know what where the carbocation is stable. Second of you that how to shift or which one we are going to shift. Migratory aptitude. Okay, and the last step is easy for you. Okay, so any problem with the question, no Jatan it or no Divesh, the C is the correct answer. Okay, so very good Lakshmi and Shiva. Okay, any problem still left, feel free to ask because it's really, really, really very much important reaction. You know, in complete class, we just discuss about only one reaction. So it's really important. Okay, really important reaction. So still, if you're having any doubt, please let me know. Otherwise, let's end the class then, okay? Okay, so thank you so much for joining the class. So phenyl with CS3 migrate because yes, of course, Niharika, you know there's a plus H group have to be there. Okay, so that's why you're right. Okay, welcome everyone, and thank you so much everyone for joining the class. Today the strength is very good. Okay, in the previous class the strength was very bad. So thank you so much again. Thanks for joining the class. Let's meet in the next class. Thank you. Have a nice day.